class, it's Patrick. Um, right now I have the Moodle page open. You can see Chapter 5, Chapter 6 are both open. I just want to warn you, for Chapter 5, the slides might look a little different. We're going to be using a different text slide for Chapter 5. And in fact, it's basically going to be a case, which you can open up here in this Word document. And this Excel sheet here is going to be walking you through that case. I like the way that this old textbook worked with this particular chapter. It kind of walks through the chapter using problems, and I think that'll be helpful for you. So instead of using your current textbook's chapter 5, we're using another textbook's chapter 5, at least for the slides. But the material is going to still be the same exact material you're learning in your current textbook. So just a different way of looking at the picture. Let's get started. If you want to follow along, you can open up the case. You can open up the Excel sheet. Again, all the problems that we'll be solving are already solved in the Excel sheet, so you can figure out from the Excel sheet how they were solved. If you open up the PowerPoint slide, just bear with me for a second. So this is Chapter 5 on discounted cash flow valuation. I typically talk about, at the outset here, the retirement situation and how important it is in the current day. We all want to retire at some point. So it's important in the business world today, and it's a topic in the news. You see this pretty frequently, and the time value of money is very relevant to this situation. I think we talked a little bit last week about if you ever have someone from your organization's 401k come into your work and talk to you about the importance of saving early for retirement, I mean, this chapter is all about that. Speaking of savings, savings in the United States is relatively low to historical norms. It's increasing slightly, but it's still low relative to what it has been in the past. This link here from the BEA provides some data on that. But on top of that, this situation on retirement and saving for your own retirement is becoming increasingly important because we can't necessarily rely on Social Security. The ratio of workers to retirees, which once was 17 to 1 in 1950, is going to be down to about 2 to 1 by 2020 and going to worsen from there. And this will cripple Social Security over time. So there's a fear that Social Security may not be there when we need it. And that just makes the relevance of saving for your retirement now that much more important. And this chapter is all about time value of money, which is, again, incredibly important to the retirement situation. I just want to also reiterate that your current textbook utilizes an example of baseball player salaries to talk about the time value of money for this chapter. Just talking about whether players should obtain, lump sum payments up front, or if they should spread it out. What's the better type of approach? This chapter will help answer those types of questions as well. So we're going to begin the chapter with a quick review. Let's start with timelines. As you can see here, we have a timeline with cash flows at time period 0, time period 1, time period 2, and time period 3. And timelines are basically showing the timing of the cash flows. The tick marks are going to occur at the end of the period, so time period 0 is actually today. Time period 1 is at the end of the first period, or the beginning of the second period. And that point on the end of the first period is actually pretty important because we're going to switch that assumption later once we get into annuities. So again, I'd like you to check out the case. That's how we're going to walk through the chapter. Just to read to you the first paragraph in the case, we're making an assumption you've applied for a job with a local bank. As part of the evaluation process, you must take an examination on the time value of money. So the first question asked by your new employer is to draw a timeline for a $100 lump sum cash flow at the end of year 2. So that's one of the first things we need to do. here's what it would look like. A $100 lump sum due, in this case, in 2 years, would look like this on a timeline, where you have time period 0, time period 1, and then at the end of 2 years, you have that $100 lump sum. The next question asks for an ordinary annuity of $100 per year for 3 years. Well, that would look like this. Here you have a 3-year $100 ordinary annuity, and you can see that the payments are occurring in periods 1, periods 2, and periods 3. And annuities are going to have that equal payment. So we're going to talk more about annuities as we move through this lecture. The third question is to draw an uneven cash flow stream of -50, $100, $75, and $50 at the end of years 0 through 3. And that would look like this. As you can see, in time period 0, there's a -50. Time period 1, there's a 100. Time period 2, there's a 75. And time period 3, there's a 50. The next question is going to ask us about what the future value of $100 after 3 years if it earns 10% annual compounding. Before we get into that, it's important to kind of review future value. So, a dollar today is worth more in the future. If that's the case, why would that be? Future value and present value are going to help us answer those sorts of questions. Future value is defined as the amount to which a cash flow or series of cash flows will grow over a given period of time when compounded at a given interest rate. And present value, the value today of future cash flows or a series of cash flows. So compounding is the arithmetic process of determining the final value of cash flows when compound interest is applied. So basically, compounding, as we talked about last week, is the process of earning interest on interest. Again, our old text has a different way of going about defining different terms in terms of what they use. You know, last week we were talking about how Excel uses N per for a number of periods. Excel uses PV for present value, just like this. These slides set FV for future value, cash flow, CF. So they're all consistent. But we used R last week for interest rate. They use I here, so it's just a little bit of a different way of going about things. They also you're going to see INT pop up a little bit in this chapter, and that's going to be the dollars of interest earned per year. Okay, so getting back to that question I was asking, which was what is the future value of an initial $100 after 3 years if the interest rate's 10%? Finding the future value of a cash flow or series of cash flows is called compounding, and the future value can be solved by using this step-by-step equation, or you could use spreadsheet methods. So we could pull up Excel and solve this pretty simply, or you could just solve it on your own. After 1 year, the future value would be $110. You would just plug that into the equation. You know, $100 multiplied by 1 plus R or 1 plus I, depending on what text you're reading. And you're going to see that it would be $100 multiplied by 1.1 is going to give you $110. After 2 years, this answer would be 121 because that 1.1 is squared. And after 3 years, it's 133.1. So our formula basically reduces down to this formula here that you see at the end. FV is equal to PV multiplied by 1 plus I to the n power. So we can also utilize this or solve for this in Excel, or, you know, the old text used to use this calculator method. Now, I've told you before, I really don't like the calculator method. It's old school. It's not necessary in this day and age. And it's funny because I just saw my wife earlier today utilizing a calculator. And at any rate, it's very old school. But you can use Excel to calculate all these things, and you don't need to actually purchase a calculator. And I told you, I think, that the textbook for the calculator, to use a financial calculator, is almost as big as the textbook for this class. So it's really not necessary. At any rate, you have different inputs here, And I do think the way this slide set works is actually kind of convenient. You have your different inputs that you're going to put into Excel, and then you're going to have your output. And in this case, as you can see here, your output's going to be that future value, which we're going to get that 133.10. So I'm going to real quick flip over to Excel, if I can, show you that it's in here. Here's our first problem. Wish there was a way to make this a little bit bigger so you could see it a little bit better. I'm trying to figure that out. Bear with me for just a second. Well, I know I can at least do this. Okay, so you see the N is 3, the interest is 0.1, present value is negative 100, payment's 0. And then we write in our future value formula, which is F equals FV parentheses. Everything pops right up. So you put in your rate, you put in your number of periods, you put in your payment, and you put in your present value, hit enter, you get your 133.10. Let's go back to the slides. In terms of present values are going to be important because opportunity cost is going to be relevant here. And opportunity cost is the best alternative foregone. The rate of return you could earn on an alternative investment of similar risk could be considered your opportunity cost. So present values are going to be useful in talking about opportunity cost. Present values are going to involve discounting, which is the process of finding the present value of a cash flow or series of cash flows. And basically discounting is the reverse of compounding. While I feel as though, I think I talked about this last week, compounding is pretty easy to understand. Discounting is a little bit more difficult to understand because it's basically compounding working backwards. Your integrated case, the Word document I was speaking about earlier, has question B2, what's the present value of $100 to be received in 3 years if the interest rate is 10% compounded annually? So finding the present value of a cash flow or series of cash flows is called discounting again. The present value is going to show the value of the cash flows in terms of today's purchasing power. As you can see, you can use a timeline to solve a question like this. You could also solve the question utilizing your formula, which is present value equals future value over 1 plus I to the n power. And if you plug all the variables in there, $100 for the future value, 10% for your interest rate, 3 years for your n, you'll end up getting a present value of 75.13. So you could also do this with a calculator, but we're not going to do that again. We'll use Excel, but this slide is useful for showing what the inputs are and what your output would be. So real quick, I'm going to go over to Excel, show you how that would be solved. Okay. Alright, so if I wanted to solve for present value again, you'd write in equals PV, parentheses, you put in your rate, you put in your number of periods, you put in your payment, and you put in your future value, you'd hit enter, and you get negative 75.13. And remember, the present value is going to come out as a negative number, not a positive number. I mentioned to you this last week several times that the reason the present value is going to be a negative is because it's going to be thought of as us putting down that money to be made the interest. So imagine you giving that money to someone to invest it, whether it's a bank or a stock or something of that nature. Okay, the next thing we talked about last week was the interest rate. So you can also solve for the interest rate. And our question in our case is, what is the annual interest rate that would cause $100 to grow to $125.97 in 3 years? Again, you can use a spreadsheet to solve for a question like this. So we go back over to our spreadsheet, go to question C here, get this a little bigger so you can see it a little better. And see here we're solving for the rate, so equal RATE, parentheses, the number of periods, your payment, which is always going to be 0. Well, we are going to change that a little later. Put in your present value and your future value, and you get 8% as your interest rate. The last thing we solve for, sorry, I don't know why this is up. Bear with me for a second here. I'm going to get rid of this. Why that's not letting me. Here we go. Okay, so the last thing we solved for last week was the number of periods. So you can solve for your n or your n perf. And doing so, the question that's given to you is, if company sales are growing at a rate of 20% annually, how long will it take sales to double? You can plug all these variables in within Excel. Let's do that. And if you do that, write equals NPER for number of periods, put in your rate, put in your payment, which is 0 still, your present value, which is a -1, and your future value, which is 2, you get 3.802. Now, keep in mind, it said double. So the truth is you could put in pretty much anything. We put in 1 to 2, but you could put in 2 and 4, and that would get you the same 3.082 answer. You could put in 40 and 80, and you should still get 3.082. So as long as the numbers are doubling, it doesn't really matter. Okay, so now for some new material. That was all a review of what we've done previously. Let's move into some new stuff. One of the things we're going to cover tonight that's different is annuities. And annuities are a series of equal payments at fixed intervals for a specified number of periods. There's two different types of annuities we're going to be discussing. The first is called an ordinary or deferred annuity. And this is an annuity whose payments occur at the end of each period. An annuity due is an annuity whose payments occur at the beginning of each period. Now keep in mind, when we started talking about this in this class about time value of money, we made an assumption that we are going to assume that things are going to occur at the end of each period. Hence the reason why you see ordinary annuity, the term ordinary, because it's following the same approach we've used all along. The annuity due, meaning it's due, it's going to make payments occur at the beginning of each period, which is changing our assumption. So your case has a question on that, and you can basically see it here. The question is, what's the difference between an ordinary annuity and an annuity due? What type of annuity is shown under the circumstances shown on that Word document? And basically, the difference between the two, again, is that the payment is going to be changed. In a sense, the payment is moving up with the annuity due from the end to the beginning. And because of that, we're going to have to solve in a little bit of a different way in Excel at this point. So if we were asked to solve for the future value of a 3-year ordinary annuity of $100 at 10%, and we know that $100 payments are going to occur at the end of each period, but they're not going to be a present value under this circumstance. So how would we go ahead and solve for this in Excel? So let's switch over to Excel. Okay, so equals FV, parentheses, put in your rate just like you would before, your number of periods like you would before. Payment now is actually relevant. This is different. Now, with annuities, you're going to have a payment stream, and in this case, the payment's going to be $100. As you can see here, the payment is being entered in as a negative. So we're putting a negative in there as the payment. Present value under these circumstances is now 0. And now we see the type term um, come up, which we've ignored in the past. So let's click on what the type is. Well, you're going to have an option in your Excel. You're going to have an option because I have a Mac. I can't actually do this, but you're going to have an option for either a 1 or a 0. The truth is, you can revert to past tense in the sense that if you just fill in nothing, it will assume a specific type. So if you fill in nothing, you'll still get the 331. If you type in 1, things change. If you type in 0, it's 331. So if you don't type in anything, it defaults to the assumption that you're dealing with things as we dealt with all along. In other words, you're dealing with things in terms of an ordinary, in this case, an ordinary annuity. But if you change this, it makes it into changing the way the payment stream is going to occur to the beginning of the period. So 1 is beginning, 0 is the end of the period. And for this question, they wanted the beginning of the period, so 331 is the correct answer. Now the second question is solving for present value of 3-year ordinary annuity. We're changing things ever so slightly because we're solving now for the present value, but it's still pretty much the same deal to what we did right there. Let me blow this up so you can see a little better. Put in equals PV, parentheses, put in your rate, your number of periods, your payment, your future value, which is 0 here. Your payment here is 100, your future value is 0. And again, what would our type be? Well, we could either hit enter right after F2 like we've done in the past. You see you'll get a negative 248. Or you could hit a comma 0, get negative 248. We're not looking at an annuity due, which if we were, we would put in parentheses, comma 1, and obviously we'd get a different answer. We're dealing with an ordinary annuity, so the answer here is negative 248, 69. Now the next question asks, what would the future and present value be if this was an annuity due? So now $100 payments are going to occur at the beginning of each period. So we set Excel mode to type 1 and solve from there. And I already showed you how to do that, but here is how to do it. Let me get this bigger. So equals FV, parentheses, your rate, your number of periods, payment, your present value, and then you would hit 1, and you get 364. If we didn't hit 1, we'd get our answer that we had previously, which was 331. Okay? So that's an annuity due. We can also solve for the present value of a 3-year ordinary annuity due. Solve for the present value of a 3-year annuity due of $100 at 10%. Again, we'd have to use the begin mode in Excel. So equals PV, rate, number of periods, payment, future value, and then a type of 1. And you get negative 273.55. Okay. So the future value of an ordinary annuity is the future value of an annuity over n periods. This is an opportune time to bring up the definition of a perpetuity. Now this is a stream of equal payments at fixed intervals expected to continue infinitely or forever. The formula for perpetuity is actually very simple. Present value equals the payment over the interest rate. That's it. All right, the next question your text asks is a 5-year, $100 ordinary annuity has an annual interest rate of 10%. What is the present value? So again, what is the present value of a 5-year ordinary annuity at 10%? So it's ordinary annuity, so we want our Excel to be normal. Go over here. I'll calculate this one. Equals PV, parentheses, you put in your rate, put in your number of periods, put in your payment, which is actually going to be difficult for me to do here just because it's blocking. So what I'm going to do is put that back. I'll solve it over here. Equals PV, rate, number of periods, payment, and your future value, and you'll get 379. What happens if it's a 10-year ordinary annuity? Well, you could do this in two different ways. You could just put 10 in here, or you could rewrite the problem. You rewrite it here, and you get 614. If you get 25 years, it comes to 907. So you can see that, you know, when the n was doubled, the present value almost doubled from 5 to 10. But from 10 to 20, which is more than doubling it, the present value didn't. In a sense, as the n grows, the present value jumps at the outset, but slowly starts to grow less and less over more and more n's. And that's why, for perpetuity, you simply take the $100 payment divided by the interest rate, and that's going to be basically the maximum at which you will see the present value, and that will come to 1,000. So again, the perpetuity is $100 divided by 0.1, and that will give you 1,000. All right, so we're going to get into actually some more interesting questions at this point. This is one of the reasons why I think this exercise is pretty good. All right, so let's say a 20-year-old student wants to save $3 a day for her retirement. Every day she places $3 in a drawer. At the end of each year, she invests that accumulated savings, which would be $3 times 365, giving you $1,095 in a brokerage account with an expected annual return of 12%. So again, she's 20 years old. She invests $3 a day, but it accumulates to $1,095 a year. And she's investing it annually in a brokerage account with an annual return of 12%. If she keeps saving in this manner, how much will she have when she's 65? So I advise you to stop right now, stop the video, and try to solve this on your own. I'm going to keep going though. All right, so the way that you'd want to go about solving this is you want to write down all your variables. So let's go over to Excel and do that. Okay, so they ask how much will she have by the time she's 65? She's 20 now, so that's how many years? That's 45 years. We know the interest rate's 12%, and we know that the payment that she's putting forth every year she's putting in $1,095. So again, the question is $1,095 over 45 years, interest rate of 12%. How much will she get for that? And the answer is, right, equals FV, parentheses, grab your rate, 12%, grab your number of periods, 45, grab your payment, negative 1,095, grab your present value. And you can see here that if she does that, so $3 a day starting when you're 20 will get you $1,487,261.89. But the big but is that's with a 12% interest rate. So the interest rate is pivotal. Now, I think the next question is pretty interesting, so let's move back to the slide set. All right. So, if she begins saving today, how much will she have when she's 65? Again, that's 1,487,262. What happens if she doesn't start saving until she's 40 years old? How much will she have at 65? So before she had 45 years to do that. Now she's starting when she's 40, which means she's only going to do it for 25 years. What are we looking at then? So you put all this into Excel, you solve for a future value. The only difference really will be your N shrinks from 45 to 25. And guess what? Her total value of savings will be $146,000, which is obviously enormously less than she would have had otherwise. And this is why when the 401k individuals and financial advisors come to your office, they try to tell you, especially they pick out the younger people and they say, you really want to start saving for retirement at an early age because it's pivotal. I mean, this is a really good example of that. Starting to save 20 years later will result in $1.3 million loss. So let's move back to the question here, which would be the next question: can she catch up? Okay. How much must the 40-year-old deposit annually to catch up to the 20-year-old? So remember, the 20-year-old is depositing $1,095 annually. How much must the 40-year-old deposit annually to catch up to that 20-year-old? So to find the required annual contribution, you want to put in the number of years until retirement. We know the goal is $1.4 million, and we would be solving for our payment. So how are we going to do that? Well, this is new. We've never solved for payment before, so it's equals PMT. As you can see, they ask for the rate. We know that it's 25 years. Our present value is 0, and our future value is $1.4 million. And if that's the case, it's $11,154 in terms of payment. That's how much you would have to start investing. That's $10,000 more annually than the 20-year-old was investing. So again, saving early matters. That's the moral of the story. All right, we're moving on to uneven multiple cash flows. Trying to think if this would be a good place to stop. Yeah, I think I'm going to stop here. So we'll take a pause here, and we're going to regroup, and we're going to finish off this chapter in the next video. And we're just going to start a bit of chapter 6, and we'll end there. So bear with me for a minute as I figure out how to stop this.